All right, so in this video, our goal is to be able to graph or make a sketch of any function. So we're going to be looking at this function where we have f of x is equal to x squared minus 2x plus 4 over x minus 2. Now, when we say that we're going to make a sketch, we want to be able to basically show all the characteristics of the function, show where it's increasing, so show where it's decreasing, so show where it's have relative maximum, minimum, asymptotes, intercepts, the end behaviors, all that. So I particularly picked a function that's gonna, be rather, you're gonna have a lot of stuff. This is not gonna be a simple one, but it's gonna be a good practice problem because this is really gonna connect all the concepts you learn in this chapter and kind of connect it also with just stuff you learn in algebra. So it's a really good problem, but it might again just know that it's gonna take a while. You're not gonna be able to do this in 5 minutes. I'll put it that way. Now, some general factors that you want to keep in mind, or when you're sketching a graph of a function. We want to know where the x and y intercepts are. We want to see if there's any symmetry, identify the domain and range, understand its continuity or where it's discontinuous, look for any vertical asymptotes, and of course in calculus we're going to be looking at the differentiability, where it's differentiable, and for that we're going to then find where there could be maxima or minima, relative extrema, and the concavity, so second derivative, points and points of inflection, and then horizontal asymptotes, so we want to see the end behavior. Now there's not a specific order that you can go about this. It really just depends on the function. I usually go about each problem in a different order. It just depends. So don't feel you have to do it in this order. It just again just depends on what type of graph you got. So again, here are just some general guidelines where I just summarize that. Find the domain, range, intercepts, symmetry, figure out the derivatives first and second where they're zero, find with the critical points, and you'll see how they relate to the inflection points relative extrema. But anyways, let's get going on this. So let's start off by just calculating the derivative, and then finding the critical points and critical values of the derivative, and find the second derivative and find the critical points and critical values of the second derivative. So here we're gonna need the portion. Let's say we're gonna need the quotient rule. I don't really like, but here we go. Quotient rule. So we're gonna have f prime of x will be equal to the derivative of the top, 2x minus 2, times the bottom function, x minus 2, minus the top function, times the derivative of the bottom function, which will just be 1, all over the bottom function squared. So we can simplify this. And so we should get 2x squared minus 4x minus 2x, so minus 6x plus 4 minus x squared plus 2x minus 4 all over the x minus 2 squared. And so then we just use some algebra. We'll get that the first derivative will be just x squared minus 6x, so minus 4x. And then the 4 and negative 4 will cancel. And this will be all over x minus 2 squared. Okay, so let's see where the first derivative is undefined and where it's 0. So f prime of x, where is it 0? So that would just mean we need to set the numerator equal to 0. So find the 0 of x squared minus 4x. And you can see you can probably see right away it's going to be 2 or 0 and 4. We can factor out that x. So then yeah, the 0 is x times x minus 4. And so you have a 0 at x equals 0. And you have a 0 at x equals 4. There's 2 zeros here. Or the, well, maybe it's called not 0. Well, zeros are the derivative, either critical values. Let's label them. And also where the denominator would be 0. So when x minus 2 equals 0. And then that would be it when x is 2. You got 3 critical values, 0, 2, and 4. Okay, now let's find the second derivative. Second derivative. We're using the quotient rule again. The derivative of the top, 2x minus 4 times the bottom function minus the top function times the derivative of the bottom function. So we're going to use chain rule there. So it'll be 2 times x minus 2 to the 1, or times 1. The derivative inside, the derivative of the inside will just be 1, all over x minus 2 to the 4th. And I think this factors out to give you 8 on top. Work it out though, just to be sure. It's 2x squared minus 4x minus 4x minus 8x minus 8. Oh yeah, because you can also factor out whoops. So what I forgot to show you this. I can cancel out an x minus 2, so then that'll just be x. So what I was doing is I was just multiplying that by x minus 1. Or no, I was just multiplying this by x minus 2 to the first. Because we can take on an x minus 2 out of the top and the bottom, and also this group. So this will just be x minus 2 to the third left, and this x minus 2 goes away. So then it's just going to be minus x squared minus 4x times 2. So it'll just be minus 2x squared minus 8x. All over x minus 2 to the third power. Okay, go. And then the 2x squares cancel, minus 8x minus plus 8x, those cancel. So we just got an 8 over x minus 2's to the cube. That works out nicely, sort of. Okay, now we find where the second derivative is 0 and where it's undefined. Second derivative of x, when is it 0? So there's gonna be no zeros, because the top has to be 0 and the top is 8, so it's gonna be nowhere. No, we can just say nowhere, no zeros. And also look where it's undefined. So find where it's undefined, so where x minus 2 equals 0, and that'll be when x equals 2. So this will be a possible inflection point. Possible inflection point. Okay, so where do we go from here? Well, we want to see where we break this. We want to see where we can test this function. We want to see where we can break up the intervals. So we know we're going to break up the intervals at the critical value, so at 0, 2, and 4, but also check for any points of discontinuity. So look for the domain, identify the domain of the function. Should usually do that first, but I'm so excited to go to calculus. So the domain, remember, just the values of the function is defined for, and it's defined for everything except 2. So the domain are basically all x values except 2. So we're gonna break up. We're not gonna be able to plug in 2 into this function. And then now we just have a set of intervals broken. Well, we haven't, yeah, our intervals broken up at those points. And again, I like to go over using rows like this. Sometimes textbooks do it the other way, but it doesn't really matter. So we go from negative infinity to 0, then 0 to 2, then 2 to 4, and 4 to infinity. And let's pick a test value. I do the test value. But pick an x value in here. So again, any x value is a -1. Let's pick x is 1 here. X is 3. And let's pick x. Let's go x is 10. Then we can see what's going on with the first and second derivatives. So we're going to find what the values of the first derivative are for those x values, and find what the values of the second derivative are. I guess I don't need this table to go out that far. Okay, so find what the first derivative is when you plug in x equals -1, 1, 3, and 10. So let's look at the first derivative equation is x squared minus 4x over x minus 2. Let me do it over here actually. So yeah, I'm just gonna be doing the work here. So I'm gonna zoom past these. I'm gonna save you some time. So go ahead and just calculate these, plug these x values into the first derivative. And I'm gonna time travel right now. All right, so when you plug in these x values into the derivative equation, you're gonna get a positive number here. You're gonna get 5/9, which is positive. You're gonna get -3, which is negative, and -3, negative again, and then less than 1, 60 over 64, which is positive. Now we're going to evaluate the second derivative for these values. So go ahead and calculate what the second derivative is when you plug these x values into the equation, which is right here. I'm going to time travel again. All right, so then when you plug in these x values into the second derivative equation, you're going to get a negative, and a positive and positive value. So again, it doesn't really matter what the actual value is. Don't worry too much about the tedious calculation if it becomes tedious. Worry about the sign, because that's what's going to tell us about the behavior of the graph. Okay, now we can get a sense of what the function is doing. So then I like to put graph of f of x here. So then if the first derivative is positive here, it means the graph of the function is going to be increasing. And if the second derivative is negative, it's going to be concave down. So it's increasing, but it's going to be concave down. Here, the first derivative is negative, so the graph is going to be decreasing, and it's still concave down because the second derivative is negative. So again, first derivative is negative here, so the graph is decreasing and concave down because the second derivative is negative. Here, it's still decreasing because the first derivative is negative, but it's going to be concave up because the second derivative is positive. And it's going to be increasing here because the first derivative is positive, and concave up because the second derivative is also positive. So this will give us a sense of what the function is doing here. So now, with this function, it's really not going to be enough to just have this, because you want to have some points on what coordinates the graph is going through. So what we're going to do next is find the local extrema, find the actual greatest and lowest values of the function. So let's see where the function is defined. So it's defined everywhere except x is 2. So here we're not here we have, I can leave another column. here you're not going to have a defined value. You're going to have a vertical asymptote. Because again, the function is not defined there. Vertical asymptote is going to be the line x equals 2. Now, let's see what's going on when x is 0. We want to see what's going on when x is 0. And we want to see what's going on when x is 4. So at x is 0, the graph is going up to the left and then going down to the right, and it's concave up on concave down on both sides, but it's going up and going down. So here you're going to have a local max at x equals 0. And then if you look where x equals 4, the graph is, going downward to the left and upward to the right. So you're going to have a local minimum, local min at x equals 4. And so let's find the coordinates of the local, let's find the actual y value and of the local max and local min, just so that makes this easier to graph. We can calculate it here. So we're going to have, it's going to be 0, f of 0. So we plug 0 into the original function. And that's not easy. That's going to be easy to calculate. That'll just be 0, 0. It'll be 4 over -2. So it'll be 0, -2. So the coordinates of the local max will be 0, -2. And a local min, we're going to have it at 4, f of 4. We're going to plug in 4 into the function. We'll plug in 4 into here. It's 16 minus 8, 8 plus 4, 12 over 2, so it gets 6. So again, local max, local min. Now we want to see the end behaviors and if there are any x or y intercepts. So first, let's look if there are any x or y intercepts. So going back to the original function, remember, let's look if there are any x intercepts. You should remember this from your algebra days. X intercepts, the y value is going to be 0. So basically, you're looking for any zeros of this equation. You want to see if you can find any zeros of x squared minus 2x plus 4. So, okay, is this factorable? And you're actually going to find that this is not going to be factorable. Can't actually factor. It kind of looks like it is, but it won't be factorable. So there are going to be no x-intercepts. So there's none. No x-intercepts. And then we just find what we want to find the y-intercept. Let me put this in a. Try to see if I can squeeze it in here. Y-intercepts. Well, there should only be one technical function. So we just find when x is 0, we just calculate the value of y. When x is 0, which we already actually got, because we already found the local max there. So you plug in 0, and you're going to get 4 over -2. So then you're going to have a y-intercept at -2. So let me actually let me crank out I got some graph paper. So let me start drawing a sketch so we can see what's going on. Fancy graph paper. I'm going to use axes here. Graphing is a lost art. I hope we'll come back. All right, so Let's draw our vertical asymptote x equals 2. That looks pretty good. This is contrast. So x equals 2. It kind of doesn't look like a 2, but okay. Now we have a local max at 0, -2, and a local min at 4, 6. Let's put points there. So 0, -2. Local max at 4, 6. Local min. So the graph is, doing something interesting. And, at the local min, it's concave up on both sides of it. So it's going to be doing something like this. And on the local max, it's going to be going like this. There's one more thing you want to be aware of. And that is, this is actually going to have a slant asymptote. So if you remember, like from your maybe pre-cal days, you would get these asymptotes where actually equations of lines. And this is we want to find the limits as x goes to positive and negative infinity. Find the end behavior, in other words. Now, this just involves the original function. Now, if you remember from the previous section, there's usually strategies where you can just divide everything by x squared, and it's going to be the leading coefficient. So you would just say, oh, it's just 1 or it's infinity, because you always have an x left. So sort of. There's one interesting rule you have to remember, so that you don't mess these slant asymptotes are up, and that's when you have a rational function and the degree of the numerator exceeds the degree of the denominator by exactly 1, you're gonna have a slant asymptote. Let me write that out. Now, so I wrote it out, formally with a little star because it's a big deal. So again, the graph of a rational function has a slant asymptote when the degree of the numerator exceeds the degree of the denominator by exactly 1. Of course, if there's no common factors you have. So let's just go ahead and define what the slant asymptote equation is. And that's just going to basically involve you just using divisions. Just divide this, going back to the pre-cal days. So let me actually do it let me do it over here so you can see how it works. So, just going to, actually like doing this. Sort of. Students dread this, but we do the house action. So x minus 2 outside the house. X squared minus 2x plus 4 inside. And we find what you multiply x by to get x squared. And that'll just be 1x. And keep the x's all in this column. So x times x will be x squared. X times -2, -2x. Subtract those go away. Drop the 4. And then what do you multiply x by to get 4? You don't really have anything here. So this is going to be your remainder, but we write it, as the denominator. So then this will be x plus 4 over x minus 2. Let me write this out. So then we get asymptote. I want to intersect my graph. So we have the equation y equals x plus 4 over x minus 2. Now recognize these are the same, equations, same functions. It's just this is written in a different way. But having this form makes it much easier, because when you take the limit as x goes to infinity of this function, let's say positive or negative infinity, you're basically just going to get x plus 4 over 0. This will be just plus 0. This will go away. This will fall apart. this will just be, x plus, 0 essentially. This number gets so small, it doesn't really matter. So your equation is that the graph, yeah, it does, it does technically go to infinity, but the equation of your asymptote is going to be the line y equals x. So let's draw our diagonal, y equals x here. And then so our function is still going to be concave up, concave down there. But now we have more of a guideline of how it's going to be looking like. So it's going to be doing this sort of thing. Right, there you go. And now that was a long one, but this is a good one because if you can do something like this, the graphs don't really get more complicated or more tedious than this. So this is a good one to study off of.